Hello, the Math Dog here. So this is a video where I derive the formula for the arc length of a curve with finite length. So this is a calculus video. So here is a curve that goes from A to B. We call this arc length of this curve, we'll call this S. So what I've done here is, and F is therefore, the way it's been drawn, is a continuously differentiable curve with finite length S. So everywhere it's continuous, there's no breaks in the curve, and everywhere a derivative exists on the open interval A to B. So what I've done here is I've broken this curve up into little sections here, and this is from x sub 0 to x sub 1, x sub 1 to x sub 2, etc. And what I've done is I've drawn little line segments between points on the curve, like so, d sub 1, d sub 2, d sub 3, d meaning distance. And I could do this forever, that's what these dots mean. Okay, so I go from x sub 0, y sub 0 to x sub n, y sub n. So a sample subinterval here, this is like from x sub I sub 1 to x sub I, so that could be any of these intervals, right, say from here to here, here to here. So here's my piece of the curve S, S sub I, and then this is the line segment connecting this point to this point. So therefore, by the distance formula, so again S sub I is the length of the arc from here to here. What I can do is I can approximate this arc length using this segment d sub I, and then I can use the distance formula to calculate the length of d sub I. So d sub I is, again, would be the square root of the difference of the x coordinates squared plus the difference in the y coordinates squared. And finally, F here is said to be a smooth curve because it is continuously differentiable. Okay, there's no breaks in the curve, there's no jagged edges like this in the curve. Alright, there's the curve again. So if we add up all these d sub i's, we can approximate the length, the arc length of the curve S. So the sum of, let's say, d sub 1 plus d sub 2 plus d sub 3 plus d sub 4 plus d sub 5, etc. So we could write this using summation notation. S is going to be the sum from I equals 1 to n of S sub I, which is approximately, this is now my d, this is using my distance formula, adding all these up, the sum from I equals 1 to n of the square root of the difference in the x's squared plus the difference in the y's squared. Okay, so then all I do to go from here to here is I'm replacing y with f of x because they are the same thing. Okay, so f is my vertical movement, f is the height of the function at any point. So this, say, is the height of this point here is y sub 1. Well, it's also f of x sub I. So that's all I'm doing right here. And then I'm changing the difference. I'm using the notation delta, which means change in. So I'm simplifying this to this, x sub I minus x sub I minus 1. I'm simplifying that to delta x sub I. And I'm doing the same thing for the change in f here, from f of x sub I minus f of x sub I minus 1, just change that to delta f of x sub I. Okay, so we have this. So now we factor out from this expression a delta x sub I squared. So under the radical sign, the square root sign, I factor out a delta x sub I squared. So delta x sub I squared times 1 is delta x sub I squared. And this, if you look at it, it makes some sense. So what happens here is if I take delta x sub I squared divided by delta x sub I squared, that leaves me with delta f of x sub I squared, which is what I have here. So I should have another parentheses right here. Let me add that. Okay, So now, well, the square root of delta x sub I squared is just delta x sub I. So I'm going to pull this out of the radical sign and put it over here. So now I have this expression. The sum from I equals 1 to n of the square root of the quantity 1 plus the square, the delta f's, let's start again here. So this is the sum from I equals 1 to n of the square root of the quantity 1 plus delta f of x sub I squared divided by delta x sub I squared times delta x sub I. Okay, bringing this over to the next page, I have this. So since f is everywhere differentiable on the open interval AB, in other words, it's smooth, and since it's everywhere differentiable on AB, it's going to be everywhere differentiable on the ith subinterval x sub I minus 1 to x sub I. By the mean value theorem for differential calculus, there has to exist a point c sub I such that c sub I falls between x of I sub 1 and x of I. And f prime of c sub I is equal to delta f of x sub I divided by delta x sub I. Now, let's talk about this a little in a diagram. So here is x sub I minus 1, here is x sub I, here is c sub I falling between these 2 points. Here is our curve s sub I. Okay, this is the secant line between these 2 points. Okay, the secant line is the average rate of change on this interval x sub I minus 1 to x sub I. The mean value theorem says that there has to exist some point on this interval where the slope of the tangent line, which is the derivative, the slope of this tangent line here is f prime of c sub I. There has to exist a point here such that the tangent line, the slope of this tangent line is equal to the average rate of change. And you can visually see this. If I go from here to here, there has to be some point on this interval where the slope of the tangent line is equal to the slope of the secant line, which is what this is saying. Okay? So the mean value theorem guarantees that for us. Okay, moving on. So again, here's our result. We'll just keep copying it so we remember it. So now I make the substitution because we've shown that by the mean value theorem, there's got to be a point c sub I where the derivative at that point, f prime of c sub I, equals the average rate of change on that interval. So we're making this substitution here. So from here to here, I replace this with this. Okay, so again, I'm replacing this with this. Okay, so we get the sum from I equals 1 to n of the square root of quantity 1 plus f prime of c sub I squared times delta x sub I. So now what we're going to do is we're going to blow n, the number of subintervals, up to infinity. So as I blow the subintervals up to infinity, so here's like a subinterval. If I keep blowing it up, these subintervals are going to get they're going to get smaller and smaller until they're infinitesimally thin. So that's going to imply that my delta x sub I, which is this measure here, it's got to go to 0. Okay, so we can say s equals the limit, that's the arc length, of n, s equals the limit as n goes to infinity of the sum of I equals 1 to n of the square root of 1 plus f prime of c sub I squared times delta x sub I. And then as delta x goes to 0, so I've got, here's my delta x sub I. As it gets in there, and somewhere on there, we've got, on that interval, we got c sub I. Well, as I get this smaller and smaller, this interval goes to 0 and c sub I is trapped in there. So c sub I has to approach the value of x sub I. So we can say this, and so now we can replace c sub I here with x sub I. So we make this substitution here. because again c sub I is going to get trapped between x sub I and x sub I minus 1, or delta x sub I. So now we have s equals the limit as n goes to infinity of the sum of I equals 1 to n of the square root of 1 plus f prime of x sub I squared times delta x sub I. So finally, by the definition of the definite integral, we can replace this expression with the integral from a to b. Remember, these are the endpoints of the interval. So you've got the big curve S. This is a to b, and the curve goes from a to b. So our final result is the arc length S is equal to the integral from a to b of the square root of 1 plus the quantity f prime of x squared dx. I'm replacing delta x sub I with an infinitesimally thin interval, which we're calling dx. Well, that concludes my presentation here. So I am in another video, for example, going to show how to use this formula to derive the circumference of a circle. So if you found this video informative and you liked it, please give it a thumbs up and consider subscribing to my YouTube channel, The Math Dog. You may share the content of this video with others. And this video I would consider usually for a Calculus 2 class, although really it's using concepts from Calculus 1, so actually you could actually put it into a first year calculus class if you had the time. Thank you and have a good day.